In this long travel that was the study of radiation effects in organisms, we went from the physics to the chemistry and then to the biology up to the medicine with radiation therapy. In the last few lectures, we will touch a kind of unconventional topic. So we will talk about the environment, if you want. First with the lecture on nuclear weapons and possible radiological terrorism, and then with the radioecology on Earth and in space. So the lecture is called the Nuclear Weapons and Ultraterrorism. Ultraterrorism is a term that encompasses all the non-conventional terrorism attacks, and in particular those using nuclear, biological, radiological, or chemical weapons. So we will describe this kind of weapons. Of course, among the nuclear weapons, we have a large experience coming from the World War II experience and successive tests, and so we will start with that one. We will see the physics of the nuclear weapons, and then we will move to also radiological weapons and their comparison with chemical and biological weapons. So this is something essentially I already said. Essentially, we will focus here with the radiological nuclear weapons. Nuclear weapons are those explosives triggered by fission or fusion nuclear reactions, while radiological weapons, also called RDD, are devices for the dispersion of radioactive material in the environment, also known as dirty bombs. But let's start with the nuclear bombs. So the energy for the nuclear bomb comes from fission, and I'm sure you are very familiar with this mechanism. Typically, the most known example is the fission of uranium-235, which is a rare isotopes of uranium. Uranium is generally uranium-238, but uranium-235 is fissile. So if there is a neutron at low energy that hits the neutron 235, this is now splitted in barium and krypton 96. These elements decay again, this one in cerium, and this one decays in krypton 94 with the further emission of 2 neutrons. The Q value of the reaction, so the delta M times C square using the Einstein equation, is 210 MeV. So it's a very high Q, which is why the energy is so high. This is how the partition, if you want, of the energy in a fission. I mean, the large part of the energy goes into the fragment, but the part of it goes in prompt gamma rays, neutrinos, beta rays, gamma rays, and neutrons. Now, if you do some calculation, 1 kiloton, the definition of kiloton is 1,000 tons of TNT. TNT is the most famous chemical explosive. I'm sure you're familiar with it. 1 ton of TNT corresponds to 10 to the 12 calories. Now, if you look at the Q value for fission, 10 to the 12 calories is the fission of 1.45 per 10 to the 23 nuclei, which means the fission of 57 grams of uranium. So that's it. I mean, 1 ton of TNT corresponds to the fission of 57 grams of uranium. The 2 bombs that have been actually used in war scenarios, many other bombs have been dropped, but only for tests, are the bomb in Hiroshima and Nagasaki that we have already described many times. These bombs were dropped at an altitude of approximately 500 meters. We will see why. I mean, the idea, but I can anticipate, the idea was to destroy as much as possible, if you want. If you drop at an altitude, the cone of action is much bigger. But one advantage, if you want, for the population of dropping the bomb at an altitude is that the fallout will be very limited, because there is no, if the bomb explodes on surface or subsurface, you create an enormous amount of radioactive dust that then eventually gives the fallout. The Hiroshima bomb was 13 kiloton, which means equivalent to 13 tons of TNT. And the Nagasaki bomb, which is not using uranium, was using plutonium, was 22 kiloton. Now, why we have the nuclear reaction? Because we need the critical mass. So essentially, of course, is not the single fission that makes the large energy. You need the 10 to the 20, 10 to the 23 nuclei to have a significant effect. To do this, you must have in a situation which is called chain reaction. So the neutrons that escape the volume must be compensated by those produced. It's essentially here, you know, the production of extra neutrons will induce more fissions. To do this, you need a large volume. So there is a critical mass. Below the critical mass, you have fissions. You have fissions also in the uranium mines. You know, normally in the uranium mines, a small fraction of uranium-238 is actually 235. There are atmospheric neutrons impinging on the mines, so you have fission of the 235 neutrons, but you don't have a bomb because you don't have the critical mass of 235. The critical masses can be very conveniently used to build a bomb, because you see, this is how the Hiroshima bomb, for example, was built. There was a subcritical mass of uranium here, and another subcritical mass of uranium here, and they were kept separated. So these two were not going to give any detonation. But then there was a conventional explosive propellant here that was fired when the bomb was dropped at a given altitude. At that point, this subcritical mass was hitting this one, and this hit was now overcoming the critical mass, and now the bomb can explode. Actually, it can explode by an atmospheric neutron, as I say, that would be enough, but just to be on the safe side, in the bomb there was also an alpha source that was producing neutrons, so that you had a continuous emission of neutrons to make sure that the explosion was immediate. There is another type of bomb that came later. These bombs were dropped in 1945 and were built in the Manhattan Project in Los Alamos by a group of US physicists, including many European physicists that fled to the United States during the Nazi time. The leader of the group was Robert Oppenheimer, but prominent figures for the construction of the bomb were certainly Edward Teller, and who was Hungarian, and Enrico Fermi, who was Italian. Later, though, the technology of nuclear fusion also developed, thanks mostly to Teller. And the fusion is in principle even more effective. You see that the type of fusions that you can have are typically deuterium on deuterium, that gives this reaction gives helium-3 and 3.2 MeV, and other fusions involving the tritium and deuterium. Now, to go into fusion, though, as you know, it's a big problem, because I mean, if we could use nuclear power plants based on fusion and not on fission, it would be much more effective and much more clean, because you don't have this heavy elements that you see already here, these radioactive heavy elements that are produced in the fission process. Unfortunately, you need the temperature of several millions of degrees. So what you normally do, you have an atomic fission bomb as a propellant of a fusion bomb. So first you explode a fission bomb at this very high temperature, million degrees, much higher than you can achieve with chemical explosive, no more than a few thousands of degrees, is enough to start the reaction in a fusion bomb, where you have tritium and deuterium available. So the most powerful thermonuclear bomb ever tested was a Russian bomb in 1963. It was an atmospheric test, so it was exposed to high altitude. And this bomb was 70 megatons. So it was more than, say, than 3 orders of magnitude of the Hiroshima and Nagasaki bomb that were in the order of 13 or 20 kilotons. Now we are 70 megatons. So it's say 3 per 10 to the 3,000 bombs of Hiroshima and Nagasaki exploding in a single bomb. So it's an amazing energy that can be released in this kind of weapons. And you can imagine, if you will see the impact on Hiroshima and Nagasaki, you can imagine the impact of a fusion bomb that fortunately was never been used in a war scenario. Okay. We will focus here on the fission bombs, of course, because those are the bombs that we know, and those are the bombs that essentially are discussed even now for tactical use in war scenarios. So it is the idea of using relatively light fission bombs in war scenarios has never been abandoned, and also for a terrorist attack used what are known as improvised nuclear device, or END. This improvised nuclear device will essentially use fission, of course. It's much more practical to do a fission device than a fusion device. In any case, both for fission and fusion, the energy is always divided in 4 channels, and the channels are blast, which is essentially shock wave, so it's an acoustic wave. It's a compression wave. Thermal radiation, which is in the region of the infrared, so it's an emission in the infrared due to the high temperature. Prompt ionizing radiation, mostly gamma rays, but also neutrons, and fallout, which is delayed. Pretty much, let's say, as a memory, you can remember that 50% goes in blast, 35% in thermal, 5% in prompt radiation, and 10% in fallout. But in reality, the partitions depends very much on the type of bomb, on the energy, on the altitude, on many factors. For example, if you go to atmospheric test at altitude higher than 30 kilometers, like for the most of the atmospheric tests done by the Russians and the Americans, the blast essentially goes to 0 because you have no more atmosphere, or the atmosphere is very thin, and then most of the energy is released in thermal and ionizing radiation. Also, for fusion bombs, the fallout is always small, is always less than 5% in any case. And the fallout, as I told you before, goes almost to 0 when you have a high altitude exposure, because you have maximum fallout when you have a ground explosion or subground explosion. This is now, you see in this movie, you see the famous movie that shows the Enola Gay airplane dropping the bomb in Hiroshima, and the view of the mushroom from the airplane itself. The famous mushroom, you see, is due to the toroid circulation of hot gas. This is the Nagasaki bomb instead. You see, again, the Nagasaki bomb seen by the airplane. The Nagasaki bomb, as I said, was a plutonium bomb, but still, you see, it's similar in terms of sucking the hot gases, and you have a toroidal circulation that gives this shape of the mushroom. Now, what is the physics behind? So the fireball is essentially the central core of the bomb, where the explosion, where the fission process occurs. The fireballs reach a temperature of about 10 to the 7 degrees, so 10 millions of degrees, in something like 1 microsecond. So it's an incredibly hot core that emits X-rays, low energy X-rays. These X-rays are absorbed in a few meters and cause a secondary emission of visible and infrared in the visible and infrared region, which is the vision that you have of the bomb. So it's caused by the high energy emission of X-rays, but these are absorbed, and the secondary radiation is at lower energy, so in the infrared and visible, and so you see the bomb. It takes about, you know, it takes about 10 seconds to see the bomb because of this process. So the fireball grows, but it can be as big as 8 kilometers in 1 minute, but cools down. I mean, in the growth, the fireball, of course, becomes cold. For a power of 1 megaton, as we have seen before, at an altitude below 10 kilometers, the mushroom can go up to 20 kilometers in less than 5 minutes. So it's really incredible. The shock wave, of course, starts immediately. We will see the physics of the shock wave, but you can imagine this is simply the extremely hot fireball that causes the shock wave, the expansion of the gas, and then the relaxation, and then the wave. And prompt nuclear radiation, gamma and neutrons, is emitted in less than 1 minute from the explosion. So this is, of course, the effect of the blast wave.
Rush to get on that tram and figure out where we were going and on the fly.
What you are seeing here is Hiroshima after the bombing. You see the river in Hiroshima, and the impact of the shock wave is clear. Some buildings are still on, but most of the buildings are wiped out. This wiping out is mostly caused by the blast wave that has destroyed completely the city. So what is the physics of the blast wave? This is the same physics that you have for any explosive. It will be the same for chemical explosive. So you can have fireball at very high temperature. This is essentially gas, of course, and at a very high pressure, because, of course, as you know, P is equal nRT divided by V. So it's a huge pressure at this point. And then, of course, the pressure variation generates a wave, which is similar to a sound wave. The speed, in fact, is about 340 meters per second in air. How do you describe the dynamic pressure? The dynamic pressure, you see, is given by the Rankine-Hugonot equation. This is well known in acoustic. You see this is the pressure, this is the ambient pressure. The dynamic pressure is given by the P is the peak pressure, actually, so the maximum pressure here. P0 is the ambient pressure, and gamma is the adiabatic constant. So is the ratio between the heat capacity at constant pressure and the heat capacity at constant volume, which is well known in thermodynamics. So it's a simple acoustic wave. Of course, because the peak pressure is so enormous, the impact is so enormous. In fact, you see, if you look at this movie first, let's look at the movie first. This is a bomb and these are trees. What is interesting in this movie is that you see clearly that after the explosion, you have the blast wave and you see the trees that bend in this direction, and then they bend back in the other direction, and then they swing back and forth. So this is the local behavior. Let's say you see, this is the overpressure as a function of the time, and this is the dynamic pressure as a function of the time. So the overpressure, you see, it's huge at a certain point, but then goes down, and this is the time of the suction. And then you have a wavy behavior, as you also see here, where instead this is the dynamic pressure, not the overpressure. So it's interesting because you see in a given point, Q goes from P0 to P and then goes back to 0. And then follows the suction phase. Now, the suction phase is interesting because it's the reason why when there is an explosion in your house, I don't know if you ever experienced it, that there is an explosion in the street, any kind of loud explosion, I mean, that can be caused, you know, by a car or by during the New Year celebration, there is a lot of small explosive. What happens that if you have the window open, the window closed, which is strange, you know, because you have the blast wave coming in, but then you have the suction period, and then the windows, boom, blam, and step back, close, and sometimes the glass are broken, not by the incoming wave, but by the suction wave. This we have seen as a function of the time. Now, if you take it as a function of the distance, of course, this is the peak overpressure, not the dynamic, is the peak overpressure as a function of the distance from ground zero for a 1 kiloton bomb. So you see, you go from some 10 to the 4 kilopascal, and then you go down, this is a log scale. So when you go from, let's say, from 100 meters to 1 kilometer, so if you increase of an order of magnitude, you see that there is a decrease of a couple of order of magnitudes in the blast wave. So of course, distance is very important. It's useful to use scaling laws, so because the physics then becomes complicated to understand what is the peak overpressure for the different bombs. It has been shown that it's approximately go with the cubic root of the power, which means, you know, that you see D divided by D ref is W divided by W ref to 1/3. And this means that to double the impact of an explosion, the energy must be 8 times bigger. So this is also why there was this rush, you know, to more powerful bombs, because of course it's not a linear scale between the impact of the bomb and the power of the bomb. You have it goes with the square root of the power, so it increases slowly. Now, what is the effect of the blast wave? Of course, depends on the peak peak overpressure. You know, so if the peak overpressure is about 4 kilopascal, you start to have window glasses that are broken. At 7, you see aluminum panels detached, wood panels broken. At 35 kilopascal is the threshold for the eardrum perforation. This is the first biological effect of the overpressure. The most sensitive organ is the ear, of course, because the eardrum is the one that keeps the pressure between the external part of our body and the internal part. So you break the eardrum with a pressure of 35 kilopascal. This can happen, you know, also with the very strong blast for other reasons. And then you see the increase at 80 kilopascal, the second most sensitive organ is the lung. At 170 kilopascal, you have severe pulmonary damage. 650 kilopascal, you have 100% mortality. And 1500 kilopascal, you even blast ferroconcrete bunkers. It's very difficult to reach this overpressure unless you are extremely close to ground zero. To have 1 million pascal. In Hiroshima and Nagasaki, only reinforced buildings were not destroyed within 2 kilometers from ground zero. And when we calculate the biological damages, we also have to consider the production of projectiles. So, of course, in the blast, you destroy and you create a high velocity projectiles like wood, stones, that can behave as bullets in a gun. So they are extremely dangerous and potentially extremely lethal. The second path that we described is thermal radiation. This is also a famous image in Hiroshima and Nagasaki. This was a bridge in Hiroshima and Nagasaki. And you see that the shadows created by the bridge and the people that were burned also created shadows. So thermal radiation is in the infrared region, is easily absorbed, but because it's easily absorbed, is the cause of fire and burning. What is the physics? The physics is also very well known. You can imagine it. Now, the fireball is essentially a black body. The physics of the black body, I think, is the start of the quantum mechanics. So I'm sure you all remember it. It's a black body. So you have to use the Stefan law. And if you remember, the Stefan law says that the power in calories per second is proportional to the fourth power of the temperature. And sigma is the Boltzmann constant. So r is the distance. 4 pi r square is the let's say is the surface of the from the point where you emit this infrared light. Of course, again, this is proportional to the power to 0.56 approximately. And if you look at the power in calories per square centimeter, so now let's say per surface unit, this is represented by this equation. You see, you can give it Fw, where W is the power, divided by 4 pi d square, which is the surface, and again multiplied by E2 minus kd, which is the absorbance of the infrared light as a function of the distance. So there are two factors decreasing the thermal radiation. One is the distance factor, because of course you distribute your energy on a sphere, so it goes down like 1 over 4 pi d square. And the other one is an exponential decay caused by the absorbance. For example, if there is a person, the person will absorb the radiation, and then you have a decrease. But also the air is absorbing. So here, these are iso-effect curves, let's say, that gives you the explosion energy in kilotons. So remember that Hiroshima and Nagasaki are here, but some bombs can go up to here. And this is the distance from ground zero in kilometers. So this is done in particular conditions like 20 kilometers visibility. Visibility is important, gives you the density of the air, and an altitude less than 4 kilometers. And this curve is for 5 calories per square centimeter, and this curve is 50 calories per square centimeter. So if you want to know the ISO effect at 5 calories per square centimeter, for a 10 kiloton bomb, like in Hiroshima, this is about 2 kilometers from ground zero. But if you go to a megaton, like the bombs in the Russian arsenal, this is actually 20 kilometers, almost 20 kilometers. So the same effect that we have seen in Hiroshima in 2 kilometers will be expanded to 20 kilometers. Now, and what are the effects? Well, this is infrared light, and the intensity, of course, is huge, because you have seen that goes with the fourth power of the temperature, and the temperature is millions of degrees. So to give you an example, if you take the calories per square centimeter, so essentially this formula, you start to have first degree burn and second degree burn of the skin for 2 and 4 calories per square centimeter. And then you see, you will start to see melting of rain capes, this plastic nail capes at 6. 7, you have dry wood fire, and then so on, pepper fire, grass fire, 3rd degree burns, cotton t-shirts fire, acetate t-shirts fire at 27. So the t-shirts go on fire. Sand explosion at 30, roof fire at 35, and even chassis blisters. You know, in the car, you make blisters at 40 calories per square centimeter. The effects are color dependent, and the white has a high reflection index, so reduces fire. There is a movie now that I want to show you. The movie that I will show you is for Nevada tests in 1953. And corresponds to approximately most of the, not everything, but most of the things that you will see are approximately 25 calories per square centimeter. So we are approximately here. After the 3rd degree burns, of course, people are killed immediately by thermal radiation. So thermal radiation, if you are exposed to, if you are not shielded, thermal radiation will be the first cause of death. Blast coming later, as we will see in a second. 35 kilopascal of peak. So this is these are the Nevada test explosions, and you see the bomb. And now, of course, the speed is different. So you see that, of course, the fire comes first, and then comes the blast. It's like thunder in a thunderstorm. You see that the flash and the thunder are separated, and same here: fire and then blast. Fire, thermal radiation, and then blast. This is a ferroconcrete bunker, you see, that resists to the fire and actually resists also to the blast and then blast. So this gives you, of course, an idea of the tremendous impact of this radiation. And now, in the second part of this lecture, we will focus instead on the nuclear radiation. So, nuclear radiation is, of course, what we care more, but we have to understand all the channels, otherwise we cannot compare. So, as I said, prompt radiation, gamma and neutrons, is emitted in about 1 minute from the blast. It is gone quickly, let's say. There is then a residual radiation caused by fission fragments, induced radioactive elements, especially by neutrons, and to a lesser extent by non-fissioned uranium and plutonium that remains in the atmosphere. Now, the local fast fallout is observed in underground, superficial, or low-altitude explosion, when fission products bind solid fragments and fall in a relatively small area. So you create them and then you have the fallout. An example was the Bikini Atoll case, where there were in 1944. In that case, was a 15 megaton bomb test at an altitude of 2 meters over water. In that case, and the production was of fallout was enormous. I mean, you see at 1 kiloton you have 10 to 21 becquerel. So in that case, the dose exceeding the lethal dose at 50% in 96 hours up to 10 kilometers from ground zero. And unfortunately, there were fishermen in the Bikini Atoll that were exposed to the fallout and died. Instead, the delayed fallout, this is the early fallout. The delayed fallout is observed only in high altitude explosion, because in this case, you can contaminate the troposphere with radionuclides and the stratosphere in months, in years. Of course, it takes, it's like a contamination of the full atmosphere. But this is real because, of course, the delayed fallout is extremely small, but is still contributing to our natural background radiation. The fallout of the bombs dropped in the 50s and in the 60s is still contributing to our natural exposure. Now, this is how the prompt radiation looks like. So you have, I apologize, some of these scales are in Italian, but this is energy of the explosion in kiloton and the distance from the explosion in meter. And these are isoeffect curves. You see, this is the fission region and this is the fusion region. These are gamma 1 gray, neutrons 1 gray, gamma 10 gray, and neutrons 10 gray. So you see increasing the energy of the explosion at which level you can go to these high doses if you want. Probably this plot is more clear. This is from Hiroshima DS-86, the dosimetry system from 1986. This has been revised many times, but I leave this image here because it gives you the idea. Is the gamma dose, this is in milligray, so you see 10 to the 4 milligray means 10 gray, as a function of the distance in meters for gamma and neutrons. So you see that both gamma and neutrons give significant doses when you are close to ground zero. Here is not even calculated because, of course, a distance lower than 500 meters, there can be no survivors anyway. So you start to calculate from here. and then decrease. This is a log-log scale. Decrease due to the again due to the attenuation in the media, and due to the geometric factor, of course, that you are distributing the energy on a sphere. And you also see that neutrons are substantially lower than gammas, but don't forget that neutrons are have a high biological effectiveness. So this is interesting. I mean, it should not be underscored that neutrons can have a significant impact. The RB, in fact, is 5 to 20 compared to gammas. So it's not negligible. In fission bomb, most of the dose is caused by gamma rays, more than 80%. But in the thermonuclear bombs not wrapped in uranium, these are neutron bombs. These neutron bombs, in this case, most of the dose is due to neutrons. The gamma rays are very high energies. Gamma rays, this is in the range of energy 1 to 7 MeV. So it's substantially higher energy than the gamma ray that we use on Earth with cobalt-60, which is 1.13 MeV. So we have to keep in mind that our standard for radiation protection that we have described last time is based on a mixed field of gamma rays and neutrons, and this mixed field of gamma rays and neutrons is relatively high energy gamma rays. Higher than, so there is always the suspicious that being higher energy, the gamma rays can be less effective than cobalt-60 gamma rays, which is only 1 MeV. If you increase the MeV, you decrease the effectivity. And this is instead the late fallout. As I told you, the late fallout comes from different isotopes, you know, very, very exotic isotopes. And this is the dose to the lung, to the gonads, to the bones. This is the collective effective dose equivalent. Collective effective dose equivalent is we will come back to this one, but let's say the dose, the dose in sievert, you see is in the order of 1.6, 0.94 to gonads and 3.6 to the bones, to be compared in 50 years. This is what you have in 50 years. To be compared to 100 millisievert from natural background. So you see it's in the order of few percent of the natural background, but it's still there. So now we have to talk about casualties. We have to talk about casualties because here there is a lot of confusion. We have seen the survivors of Hiroshima and Nagasaki, and it is important to, also for terrorism reasons, it's important to clarify how many people dies and how they die. It's a little bit sad, but it's necessary. So you see, this is Hiroshima, so 13 kiloton, 500 meters. And Nagasaki was 22 kiloton, 490 meters. Is divided in groups, a distance from ground zero less than 1 kilometer, less than 2.5 kilometers, and less than 5 kilometers. Over 5 kilometers, you had almost no casualties. The density of inhabitants is given here, and the total, you see, this is was higher in Hiroshima than in Nagasaki. The exposed persons, again, was much higher in Hiroshima than in Nagasaki. We're talking about some 250,000 people in Hiroshima and some 170,000 in Nagasaki. And the victims were about 68,000 in Hiroshima and 38,000 in Nagasaki. This is the wounded. Of course, you see that at low distance, a small distance from the ground zero, the victims are almost the same as the exposed. But if you go to 5 kilometers, let's say between 2.5 and 5 kilometers, you have a majority of survivors compared to the victims. So in total, you see the victims of Hiroshima and Nagasaki are about 100,000 people. So Hiroshima and Nagasaki, forget about the legends. Hiroshima and Nagasaki together made 100,000 people. Now, I don't want to discuss whether this was right or wrong. You know, there's a long political discussion and also strategic discussion of whether this was worth to kill so many innocent people, civilians, to save the life of presumably many more in a conventional war. But my point from the terrorism point of view is to understand how big is this number. And to do that, I tried to collect in this slide. Oh, I'm sorry. First, let's say the death cause distribution. Death cause distribution, you probably know, this is in this pie plot is more than 100% because, of course, you have overkill. So many people are killed both because of thermal radiation, prompt radiation, and the blast wave. But you see, you have like in this non-normalized plot, you have most of the people are killed thermal radiation and blast wave, some 30% by prompt nuclear radiation, and some only 0.4% by late radiation effects. Which again, you have to keep always in mind, the idea that many more people died because of late radiation effects compared to the early effects of the bomb is simply ridiculous. We are talking about some 0.4%. Now, as I said, now I want to compare the different cause of death, comparing Hiroshima and Nagasaki with other events that cause large number of casualties is a nice canvas from Peter Bruegel, a Dutch painter from the 16th century, which is in the Prado in Madrid. It's called The Triumph of Death. It's interesting because you see that in The Triumph of Death, people are mostly killed by wars and by pandemics, epidemic. You see that the Black Death, the plague, and the wars that are killing the people. And as a matter of fact, this is now a, if you want, it's a slightly controversial slide, but I found it important. Let's see different events in different years in the history of mankind and estimated deaths in thousands. So we have seen that for the atomic bombs in Hiroshima and Nagasaki, we are in the order of 10 to the 5 casualties, 100,000. In the same order of magnitude, you see events like the tsunami in the Indian Ocean that probably you remember, you were probably very young, but probably you remember around Christmas in 2004, there was a disastrous tsunami in the Indian Ocean that caused 2 times the casualties in Hiroshima and Nagasaki. Then you have war, the Nanjing massacre in China in 1937, done by the Japanese, 300,000. The Darfur genocide in Sudan, much more recent, 350. Something very familiar now, the COVID-19 pandemic, up to a few days ago, I think it's growing and growing, but up to a few days ago were 470,000 casualties. Compared though to the earthquake in Tianjin, it was only in Tianjin, but was one of the most devastating earthquakes in the history, recent, 1976, it did more casualties than the COVID-19 pandemic. Probably the COVID-19 pandemic will exceed 500,000, but at the moment. And also a war like the Battle of Stalingrad in Russia made 670,000 casualties, a single battle. Now, let's go to the next order of magnitude, in the order of 1 million. Then we have again war, the Armenian genocide in Turkey. About 1 million people were slaughtered by the Turkish million. The flood, so natural events complicated by the negligence of humans. You see in China again, 3.7 million. And then we start to see the biological, the COVID this year. We have seen the COVID already, but in the past, one of the worst infecting agent was the plague, Yersinia pestis, which is a bacteria which is delivered generally by the fleas. And one epidemic was the Antonine plague during the Emperor Antonin. So in the 2nd century after Christ, 4.5 million estimate. These estimates are very, certainly not very accurate, but to me, it's interesting only the order of magnitude. Then the famine, for example, in Ukraine, during the Soviet Union, there was an attempt, you know, to decentralize, to eliminate, to get rid of all the private peasants, and this caused a famine. That time there was Stalin, 5 million. The Jewish Holocaust, you know very well, 6 million. Then we go to 10 to the 7. Again, plague. This is a pandemic in the 19th century, so relatively the most recent pandemic. This made 10 million casualties in China and India. The whole World War I made 20 millions, far less than the Great Leap Forward famine in China in the end of the 50s, which was caused by the idea of Mao that China had to become a superpower, so they had to produce steel, and then all the people were producing steel, were melting steel in the countryside, and there was no harvest, and then there was a terrible famine with more casualties than the World War I, but still less casualties of the Spanish flu, which is now very well known. Everybody's talking about the Spanish flu. Actually, the Spanish flu did 40 million casualties, more than the world, almost 2 times the World War I, and lasted quite a lot from 1918 to 1920. Hopefully will not be the same with COVID-19. We are still here. World War II itself made 60 million casualties, approximately. Far less, in any case, than this is the man, if you want. So World War II is the man, Great Leap Forward is the man too. I mean, it's the stupidity of man. World War I is the man. So all these are marked as human mistakes, but the Spanish flu and all the leaders, the bronze medal, silver medal, and gold medal are all biological weapons. You know, in particular, this plague, and it's the Black Death plague in China from in the 14th century that made some 65 million casualties. And then the same plague came to Europe, where made another 75 million casualties. It came in the ships coming from the east, mostly carried by rats. And finally, probably the world record with large uncertainties, I have to say, but in the order of 100 million casualties was the Justinian plague during the Byzantine Empire, so in the 6th century, that killed some 100 million people, which is corresponding to between 1/3 and 1/2 of the overall population of the Byzantine Empire at that time. So it's this is kind of considered an event. It's much longer than this. I mean, this was the peak, but then lasted for almost 2 centuries, this plague, and is considered one of those events switching from the Middle Age to the modern time. Why I show you this to you? Because you see clearly that the atomic bombs are relatively low in terms of capability of creating damage, and the biological weapons are definitely those with the greatest potential. This was maybe not obvious to students of last year and in the previous year, but I think it's pretty obvious now that we have seen how the SARS-CoV-2, which is not highly lethal, of course, we all know it's not like the plague that was enormously lethal. Essentially had the fraction of lethality of almost 100% of the people that were infected. Certainly this is not the case for COVID-19, but how powerful biological weapons can be. This is important for the terrorism discussion that we will do in a second. So, radiological terrorism. Of course, radiological terrorism, the ideal scenario for a terroristic organization will be to steal or build an atomic bomb or an improvised nuclear device. So something, let's say, of less impact, but still based on the atomic bomb principle. If you cannot do it, you have alternatives, and these are radioactive poisoning, attacks on nuclear power plants, contamination of drinking water, a radioactive dispersal device. And in the second part of the lecture, we will discuss these different devices and how they work and how, in principle, they can be used in terrorism.